Alright, so let's suppose that we have a very long, thin particle, and it's very small, so it's being buffeted around by Brownian motion. So one example of this is there's from biophysics. There's a virus called FD virus. All right, it's just very long and thin, and has a long persistence length, so it's pretty stiff, and it's of course only, I don't know, something like 7 nanometers across or something. All right, so it's just a long, thin particle that if you put it in water or whatever, it will jiggle around just with Brownian motion, just due to just the thermal energy, right? So what we want to know is the angular momentum of this, if it's in thermal equilibrium with its surroundings, which angular momentum is larger, the spinning of the virus or particle, or the rotating around one of these other axes, or either one. So basically, is its angular momentum vector closer to the z direction, or meaning parallel to the length of the rod, or is it mostly perpendicular to the length of the rod? All right, so anyway, is the thing rotating this way, or is it spinning that way? All right, so if we look at the rotational energy, let's say for the x direction, so we have a 1/2 I sub x omega sub x squared. All right, and same goes for the y and z. I sub y omega y squared equals 1/2 I sub z omega z. Oops, that's a z squared. All right, and because this is in thermal equilibrium, each of these is going to have, each of these has 1 degree of freedom, right? So we have an amount of energy of 1/2 kBt. I mean, it doesn't really matter how much they have. The point is that they're all equal under thermal equilibrium. So if we can ignore the 1/2s, right? We have this situation where we have Ix omega x squared equals Iy omega y squared equals Iz omega z squared. All right, and we also know that let's just say this thing is symmetric, whatever, so there's no difference between x and y. All right, so that would tell us that for the moments of inertia, the moment of inertia for rotation about the x-axis is equal to the moment of inertia for rotation about the y-axis. All right, and we also expect that it's going to be much greater for these 2 directions than for z. It's very thin, right? And so there's the rotational inertia of mr squared. If you integrate that, there's a lot more mass way out further from the center of rotation for these 2 directions than there is for this. All right, so these are, I'll go ahead and say much larger All right, so let's just look at one of these examples. Say, let's look at the x direction versus the z direction. Because of the symmetry here, we'll know that whatever we can say about the x direction angular momentum, we can also say about the y direction angular momentum. All right, looking at these energies again, let's just look at x. So we have ix omega x squared equal to I z omega z squared. All right, so if we were to solve this for omega z real quick, I'll put this in absolute value signs because we're taking the square root of a square. Okay, so we'd get from this side, we'd get an ix divided by divided by iz, and this is all under a square root, multiplied by absolute value of the angular velocity in x. All right, so now now we want to look at the angular momentum, right? So angular momentum I z omega z. Oops, that's an absolute value sign. All right, I'll just call that LZ. Okay. So we're looking at this. So what I need to do here is multiply this also by IZ on this side. All right, which will take out the square root on the bottom and replace it with a square root on the top. So we have an IX, IZ, and these are both under a square root. And then absolute value of the angular velocity and x. All right, so the question is, how does this compare to Ix omega x? All right, so what should go right here? And like equal sign, greater than, less than. That's what I'm talking about. Okay, well, I sub x, right, is just I sub x multiplied by I sub x, right? So an I sub x squared under a square root. All right. So since we have this IZ is much smaller than IX, all right? So that means the square root of I sub x times I sub z is also smaller than the square root of I sub x times I sub x. So this is a less than sign, all right? So the angular, so what this tells us is that the angular momentum LZ equal IZ is less than, possibly much less than the IX. All right. So it's less than, but only, you know, by the factor or the ratio of the square roots. Okay, not by this full-on ratio of the angular of the moments of inertia. So the difference is large, but not as large. It goes as the square root of this difference, or the ratios do. All right. So like we said, this x and y, they're about, they're symmetric. All right. So anything we've just said about the x will also apply to the y. So LZ. So what this says up here, LZ is less than L sub x, but also less than L sub y. All right, so that just tells us that in thermal equilibrium under Brownian motion or whatever, one of these long rod-like particles is going to, most of its angular momentum will be perpendicular to its long axis. All right, so very little angular momentum will be actually rotational, rotation around this axis of symmetry. It's going to want to turn, well, a pen is a good example. It's going to want to turn like this and not spin like this. So as far as the angular momentum goes, this is going to be much larger.